Yeah, today let's introduce the matrix algebra. It's just a review. We are using matrix, right? Matrix is very useful for what? When we are using the matrix, especially in mechanics. Nobody answer. Okay, so usually in mechanics, we have a lot of linear system, right? Then, so many equation of linear equation, it looks like that. x1, x2, 1. We have three unknown, x1, x2, x3. And we have three equations. For example, so each equation is a linear equation. And so we are saying this is a set of linear equation. A set of linear equation. First linear equation, second and third linear equation. So all these three equations give us just one set of equations. So here, what's the unknown? Unknowns x1, x2, x3. In physics and mechanics, we need to solve this kind of linear equation. And solution is x1, x2, x3. We wanted to find that x1, x2, x3, right? x4, yeah, sorry. So I need to change x3, right? And to express that set of linear equation, we can express, instead of using that three equation, we can use matrix. 3, 1, minus 1, 2, 6, minus 3, 1, minus 1, minus 1. x1, x2, x3 equal 1 minus 2, 4. So when we express the a set of linear equation, we are using matrix. This is a and with some character, A is a matrix, X is an unknown vector, and B. Here we are saying A is a coefficient matrix. X, unknown vector. And B, vector O known quantity. And the matrix A looks like this in general. It has a component A11, A12, something like that. A n 1n. Sorry. One n A 2 1 A 2 2 something like that. A 2 n A m 1 A m n. So this matrix have a row n, column n. So this is column, and this is row. Row, not L, R O W. So M equal number O row, N equal number O column. And here we are saying, this is important, Aij. So Aij means I is changing from 1 to m, j is changing from 1 to n. This is a name, is component. Component O matrix A. So you remember the vector. Vector has a component, right? V1, V2, V3. Matrix have also component. I and J is index. So basically, matrix and vector have a same form. Only difference is vector have a 1 index and matrix have a 2 index to represent their component. Especially in structural mechanics, the matrix we are dealing with is a square matrix. So M and N is the same. So 3 by 3 matrix, 10 by 10 matrix, and 100 by 100 matrix. Matrix is usually square. Okay. Then let's see a little bit special matrix in 3D geometry. In 3D geometry, we express vector x with a tensor form xi, right? I is changing. I equal 1, 2, 3, right? I equal 1 means x direction. 2 means y direction. 3 means g direction. You can understand like this. And this means x have a component xi and some given coordinate system defined by base vector ei. And we omitted the summation. Right? Okay. So let's say, how about matrix? Matrix A can be expressed by in tensor form like Aij, right? Here I and j is changing from 1 to 3. Both are changing. So this and both are tensor form. So one question is that in vector, we have a component and base. This is a base vector. But how about the base of a matrix? So we need to generalize this concept, component and base concept. Okay, we can do that. Okay, let's see how to do that. So vector A also can be written by summation I equal 1 to 3, j equal 1 to 3, and component Aij and base Ai Aj. Okay, this is a component. This is base. Or by using the summation convention Aij, Ei, Ej. This is a base. Okay. Actually, this is a base vector, a base matrix. Here, this is base vector. This is base matrix. And name of this is a tensor product. Okay, this is a sum special operator. So let me define the tensor product. So Ei tensor product Ej equal Ei transpose Ej. What's this? What's the result of this? Okay, so for example, E1, let's say calculate E1, E2 equal E1 transpose E2. What's this? E1 transpose mean, okay, 1, 0, 0. And E2. Sorry. So transpose should be here. Transpose. Okay. E1. E1 is something like that. 1, 0, 0. Here E2. 0, 1, 0. Watch this. Okay, if I calculate this, we can have a 0, 1, 0, 0, 0, 0, 0, 0, 0. We can have a matrix, right? This is not a dot product. Dot product give us dot product vector product, tensor product, all the operator about vector, right? And dot product give us scalar value, right? How about the cross product? Cross product give us vector as our output. How about tensor product? Tensor product give us matrix, something like that. So, for example, let's see when I equal 1, j equal 2, we have a matrix which have a 0 component except for the position corresponding to A, 1, 2, right? Okay. Then A equal Aij, Ei, Ej equal A11, 1, 0, 0, 0, 0, 0 plus A12 A33, something like that. Now you understand, right? What's the tensor product and what's the base matrix or matrix, okay? So we can keep the same concept, okay? For vector, we have a component and base. For matrix, we can have a component and base, too, right? So, this is tensor form of the matrix. Then, as I said, vector is a first order tensor, matrix second order tensor. Then we can define third order tensor. How about third order tensor? What's the third order tensor? Yeah, let's define third order tensor A with the 3 on the bar equal A, I, J, K and E, I, E, J, E, K. This is a third order tensor. In this sense, we can define fourth order, any order of tensor, right? So, in first order tensor, we have a one-dimensional array. And in second order tensor, in matrix, we have a two-dimensional array, right? So we put the number in some x and y direction in 2D. How about the third order tensor? We can put the matrix in 3D. We can make some room something like that. And we can put a number here. And this is a I, maybe J, K, right? That's just graphical representation. And also we can define poles. Any order of tensor. But usually in structural mechanics, we only use second order tensor, so matrix. And sometimes we need to use a fourth order tensor. Okay, so I think you understand the general concept of tensor. So when the coordinate system is given, we can write the tensor form instead of A. We can just use its component form. So if you see some quantity expressed by Aij, you can think, this is a matrix, okay? If there is some quantity Ai, this is vector, okay? Both are exactly the same thing. Okay, so sum C equal A plus B. So Cij equal Aij, Bij. So this is summation of a matrix. Sum of matrix A and B equal to C mean each component Aij plus Bij is the same to the component Cij, right? And scalar multiplication. Okay, here. B equal alpha A mean Bij equal alpha Aij. Very simple, right? This is just direct extension of vector calculation and matrix multiplication. This is a little bit complicated. A equal B, C. Aij equal Bik, Ckj. Here we have a K. Okay, here let me ask the question. Okay, matrix C is a 3 by 3 matrix. A should be a 3 by 3. B should be a 3 by 3, right? Let's assume. Then, how many equations we have expressed by this one? How many equations? 9, right? Because I and J is changing on the left-hand side and right-hand side, both. Then how about this? A and B are the order 3 by 3. How many equations here? 9. Okay, so how about this? How many equations? A, B, C are 3 by 3. How many equations? Same, 9. Then what's the K? K is changing. So this means sum K equal 1, 2, 3, Bik, Ckj. Okay, so let's say I equal K, K1, 1, I1, I1, C1, J plus B, I2 C2J plus B I3 plus C3J. Okay. This equation means this summation about the K is omitted. So you should be able to identify what kind of summations are omitted, and then, okay? Any question? Too simple? So you need to prove that in your homework number 1. Okay. And identity matrix. What's the identity matrix I? What's the identity matrix? Which has a 1. On diagonal component and 0 in off diagonal. So this is a 1. So in tensor form, we are using sigma ij. Its definition is if I and j is same, this is a 1. I and j is different, 0. So name of this is Kronecker delta. Yeah, this is quite important. We are very frequently use this Kronecker delta. Also, Kronecker delta can be calculated by base vector of Cartesian coordinate system, right? Same thing. In Cartesian, this is dot product. Okay. EI is base vector of Cartesian coordinate system. So these vectors are unit and normal to each other. So if we take the dot product of same vector, then we have 1. Take the dot product for different vector, we have 0, right? Okay. And finally, a set of linear equations. So a set of linear equations is this, right? So we can use a tensor form, yj, xj, ei. Okay, so let me ask you one more question. Let's say matrix A is a 3 by 3 matrix. Then how many equations we have in this tensor form? How many equations? 9? 3? You 9 or 3? 1. Why? Huh? Yeah, right, 3. These 3 equations. Because matrix B have only 3 components, X is equal 3 components. So when I equal 1, it gives us first equation, 2 second equation, 3 third equation. That's it. Okay, so any question? Because I like to finish the basic mathematics on vector, matrix, and tensor. I'm sure you have a concept of this generalized quantity, tensor. Question? No? Okay, so then I like think you 100% understand. Okay, so in this lecture, I like to use vector, matrix, and tensor together, all together. Deformation and strain. So, in this class, the first subject we like to study is just deformation and strain. This is all about the geometry. First of all, let's define the coordinate system. So in geometry, to define the coordinate system is very important and basic. So let's define the Cartesian coordinate system given by three base vectors E1, E2, E3. And this is origin, O. And component in E1 direction is x1. E2 direction, x2, E3 direction, x3. So based on this Cartesian coordinate system, we can define any position of a material particle in the space. 3D space, right? We are living in 3D space. And let's say we have a body here. This is a body. Body consists of lot of particles, right? Our human body also made by lot of small particles, right? Small particle. And this one has made by lot of particles. Let's say this is the initial configuration. And after some time, this body can move and deform. And then this body is a current configuration. So let's say there's a point here, okay, at the position uppercase X. X is a position vector which present the position of some material point. And this is a material point. And after deformation, this position will move to another point. And that point have a position vector lowercase x. Right? And initially the original body have a volume omega 0 and current body have a volume omega t. Well, we can say this is domain or volume. Okay? Let's say initial configuration is a time 0, time t. Let's use a concept of time. This is a very usual representation of deformation. Yeah, let's say this is a vector u. Then we have a relation. Initial position plus, okay, difference between two positions, u equal x. Very simple vector notation, right? Yeah. Because this vector plus this vector is same to this vector, right? And in other words, u equal current material position minus initial material position. We are saying this u is a displacement vector. So now we can define the displacement. What's the displacement? Huh? What's the displacement? Displacement is a difference between two positions, initial position and current position. Displacement is just difference between two material positions. Okay? Of course, the x is also vector. So x1, x is a component, x1, e1 plus x2, e2 plus x3, e3. And small x, x1, e1 plus x2, e2 plus x3, e3. And u, displacement, u1, e1, u2, e2, u3, e3. Right? In tensor form, we can write down that equation. Nu I equal xi minus x capital. xi. This is a definition of displacement. So, if we know the displacement and if we know the initial configuration, we can calculate the current configuration, right? Okay, and now let's consider some vector here. Let's say we have a vector. Position is the point is defined by just one coordinate, one position. Then to define the vector, how many points we need? Vector have a direction, right? So at least we need to know the two positions, starting position, ending position, right? And then this vector will be also changing, something like that. So, for example, this vector is something like we have here Lubo panel here. So here Lubo, you can think this is some Lubo panel, very easily expandable, and you put some Scotch tape here, and if you extend and then move, the direction of that tape is changed, the length is changed. So vector is something like that. And let's define the very small vector, dx, in initial configuration, dx. So let's define x, material position, at time 0. X is material position at time t. Okay. dx is a material vector at time 0. Here the D mean, this is differential operator D, right? D mean very, very small. So this means very small. Very, very small. So you can think this material vector is a very small vector. Very, very small vector. Okay? The magnitude of that vector is very small. Okay, so I'll continue the lecture in the next Monday. Any question? No? Okay, thanks.